Hi all. Due to a small technical issue, this initial portion was not recorded. More precisely, my absent-mindedness, it wasn't recorded. So this is just the beginning announcement of the lecture. This lecture is on exchanging limits with integrals and derivatives. This is related to what we discussed last Wednesday when we were exchanging the order of two limits. So in that case, we were, say, talking about limit as n goes to infinity, limit as m goes to infinity, s and m. And we were talking about when can you exchange those two. And the theorem we stated in that case was for a limit of the form where you have a sequence of functions converging to some function. When can you exchange these two limits? And we saw that the importance of some form of uniform convergence was needed. Now today we will talk about specifically limit of integrals of fn and when can you pull the limit inside the integrals, or limit of the derivatives fn and when can you pull the limit inside the derivative operation, namely express that. And the lecture will consist of two parts, and they're split on YouTube. One is discussing examples that discusses different behaviors with regard to integrals and derivatives. This is also the portion that may be useful for Friday because it discusses examples of uniform and pointwise convergence. And then we'll state some theorems about what actually is true, which preclude these counterexamples, and we'll prove the integral version of that. The derivative version is done on Wednesday. Now, we saw this meme on last week about one does not simply exchange order of limits. So today's theme, you could say, is exchanging limits and derivatives, or limits and integrals. Okay, so 3 questions up to today. We have a sequence of functions, and I want to say that they are continuous. You can formulate some of these without the continuity assumption. But if you don't do that continuity assumption, then you have to be a little bit careful. And mainly this is an issue with some integrals being defined. So for this class, I will just impose this condition on continuity. You will see some discussion in Rudin and Pew, if you do read those, where you don't impose this, but things get a little bit more technical. So you're free to assume that things are continuous. And then the setting is that fn converges to f with some assumption. You can impose a weak assumption such as pointwise convergence. Usually in that case, things fail. Or you can impose uniform convergence, in which case things work out. Okay, so the 3 questions that we will discuss, actually we'll discuss 2 of these questions and I'll mention the 3rd one. So if fn are differentiable, and then is the limit function also differentiable? And if it is differentiable, can you compute the derivative of the limit by taking a limit of the derivatives? So notice how this is, you have the limit on the inside, fn, and the derivative on the outside. And this is kind of passing the derivative limit inside the derivative and vice versa. And then the same question, is the limit function Riemann integrable? And if so, can you pass the limit inside the integral? So if you take the limit of the integrals, is this the same thing as taking integral of the limits of fn of x? And this is now the limit function is f, so this is the same thing. Now, relating to what I said about the issue of continuity, this really is related to a 3rd question one could ask, and this would make question 2 look a little bit more symmetric, but we'll get to this point later, is that, and I will not discuss this too much now, and if you want, Pew and Rudin, if fn are Riemann integrable, is the limit function Riemann integrable? And if it is Riemann integrable, does this equation hold. So that's more technical. In our case, Fn are assumed to be continuous, so they're automatically Riemann integrable. And this integrability of the limit function issue, that will be sort of a very short issue for us. It's good to keep in mind that this is a small question and you could ask this, but I will dismiss this mostly in this lecture. Okay, so examples relating to these questions, question 1 and question 2, about why not simply exchange and counterexamples to being too naive. So with regard to integrals, first of all, you shall not pass the limit into the integral without doing some checking. And there are a few classical examples about this. And this is also a help going through these. We'll also review some things for this Friday's midterm, because you have to there talk about pointwise and uniform convergence. So let's look at what happens here. So the first example is so-called, it's related to shifting, or sometimes called the moving wave. And you can think of this as you have some function and you're shifting the parameter. So here g of x is 1 over x squared plus 1. And you want to choose some function that is integrable on the whole space R. And what this looks like is that, okay, what is g of x? G of x is this bell-shaped thing. It has a horizontal asymptote and infinity. It's not the Gaussian bell shape, but very similar to that. It decays a little bit slower at infinity. And this x minus n, what it's doing, it is shifting the peak to the right. So Fn, what it looks like is this. And as you're shifting, as n increases, this wave kind of moves further to the right. If you had a plus there, it would be moving to the left and would have the same effect. Okay, because this wave is moving to the right, as n goes to infinity, eventually the wave disappears. So let's look at what therefore the limit is. The limit of Fn of x is the limit as n goes to infinity of 1 minus x minus n squared plus 1. And well, as n goes to infinity, the denominator, say by opening up the parentheses, it will have an n squared term there. It will go to infinity, and therefore the fraction will go to 0. This is if you fix an x. So pointwise, the functions converge to 0. Now, question, is this convergence uniform? Well, no, because if you look at the difference, if you look at this difference between these functions, then there's always a point where the difference is of the order 1. So if you take the supremum over all R of the largest difference between the limit function and f, then this is equal to 1. Well, not, yeah, it is equal to 1, because there's always this peak where f of x peak is equal to 1, namely x is equal to n here. So the distance in this uniform norm is always 1, and these functions are not converging uniformly. It's good to do that carefully if you find that at all confusing. But now let's look at what about the integrals? What happens to the integrals? Okay, so we first compute one way, limit of the integrals. Well, this is limit of this expression. And then let's do a change of variables here. This is the standard trick with a moving wave. If I shift, these functions come from a shift. So if I shift them back, then what I get by a change of variables, y is equal to x minus n. Then I get the integral 1 over y squared plus 1. And this integral is a familiar thing from calculus. It will give you pi over, first, each of these integrals will give you a constant. If I remember correctly, it gives you something like arctangent as at infinity minus arctangent at minus infinity, and I think that is pi. And now this is a limit of a constant sequence, so it's just pi. So, I mean, pictorially, you're shifting this function. Each of these has the same area under the graph. But this is the rigorous justification by change of variables and stuff like that. Okay, if we do it the other way around, so minus infinity to infinity of the limit, then we have the integral of the limit function, which is just 0, because f of x is equal to 0. So these are not equal. And the reason for this phenomenon, what issue is happening here, is that somehow one way of expressing it is that mass is going to infinity, escaping or going to infinity. It's shifting away. Any questions at this point? Okay. Now let's do another example. I mentioned this in one of the lectures videos for Friday. This is also an example that appears in Pew. I believe it also appears in Rudin somewhere. There's a standard example of a sequence of functions that has interesting properties regarding convergence, and this kind of a squeezing out of a part. And it's a piecewise function. It has 3 parts. It looks like this hat, but the formulas for the hat are a little bit irritating. So between 0 and 1 over n, it will grow linearly from 0 to n. So it has slope n squared. So the red part would have formula n squared x. The green part here has slope minus n squared, and it goes from n to 2 over n, to 0 at 2 over n. So the formula for that would be, well, it starts off at n, has slope also n squared, and starts from 1 over n to decrease. So this is a way to get the formula for that. And then the last part is just constant 0. Okay, so it parameterizes this function, and what's happening in this sequence is that this peak here is becoming taller and taller, and it's being squeezed out. So first it looks something like that, relatively wide. After that, it progressively becomes steeper and steeper, and sort of is squeezed out in the limit, because what happens in this limit is that eventually any other value will be equal to 0. Specifically, if you look at the pointwise limit, so you fix an x in 0, 1, there are 2 cases. X is equal to 0, but when x is equal to 0, this is a fn of x. They're always equal to 0. So limit as n goes to infinity of fn of x is equal to 0. And in case 2, if you are in the half open interval 0, 1, then eventually this peak will squeeze away from that. So there exists a capital N such that x is bigger than 2 over n. But then if n is bigger than 2 over n, then we have that fn of x is equal to 0, which is the same thing as saying fn of x minus 0 is less than or equal to epsilon for all epsilon positive. So this claim is the same thing as saying that limit as n goes to infinity of fn of x in this case is equal to 0. So this limit here is actually 0. Now, a small remark here is that at this stage, the choice of n depends on x. so not uniform. Also, these peaks are very high, so the difference of the functions is very large at some points. Not all points, but at some points, the differences are very large. So it's not converging uniformly again. And rigorously doing that would require a little bit more steps. But okay, let's compute the integrals again. Now, if we compute on the outside, then by calculus, okay, you could integrate the piecewise function, but it's easier just to use geometry in this case, which that this is the area under this triangle. It speeds up our calculation a little bit. So it's a triangle of height n with base of size 2 over n. So the area under the graph is n times 2 over n over 2. So it's equal to 1. And this limit of a constant again is equal to 1. But the limit of the limit function, the integral of the limit function, is equal to 0. 1 is not equal to 0. Again, we see that there's an issue, and the issue in this case is that mass is being squeezed out. And the sequence Fn is not bounded, because that's essentially the only way of squeezing it out is by making the height to go to infinity. This is part of this dynamic. Okay, any questions on these integrals? Integral examples.